So welcome to all of you. So in the last lecture we have seen what do we mean by equivalence relation. Okay. So equivalence relation is what? A relation which is reflexive, symmetric and transitive. Then that relation is called a equivalence relation. We have seen some problems on the equivalence relation. We will see one more problems on the equivalence relation. So we have given the problem what, that M and R means what? The set of all n by n, that means the square matrices of order n over R, that means each entry of the matrix is a real number. Okay, so this M and R means what? The set of all square matrix of order n over R, that means what? All the entries of the matrices are real numbers. Okay, so we have given the relation is what? AB, these are the two matrices in this set and they are related if and only if there exists an invertible matrix P such that B is equal to P inverse AP. Right? So that means A is related to B. There exists some invertible matrix P such way that B is equal to P inverse AP. Right? So what is the question? You show that it is the equivalence relation. Okay? So we take a solution. Given that Lord, given that Mn over R is the set of all n by n matrix over R. Okay, so over R for AB belongs to Mn R, A is related to be if and only this. Okay, so first reflexive. Okay, so reflexive means what? A is related to A, right? A is related to A. That means what? So see, A is equal to, right? So P inverse AP. Is it true? So if this is true, then we are true now. Okay. So that means what? If there exists an invertible matrix. See, for A. So this is what identity inverse A is identity. So you know that identity matrix is always invertible. So that means what? There exists invertible matrix I such that A is equal to this, right? So therefore A is related to A, and therefore theta is reflexive. So this is what? There exists invertible matrix. Any matrix is there, right? So there should be exist an invertible matrix, right? Such way that this property holds, right? So P is not a proper actually. You can take any matrix instead of the P, right? So it's reflexive. I call this as A now. Okay. Now second, symmetric. Okay, so let A related to B. What does this imply? There exists invertible matrix P. I can take P such that A is equal B is equal to P inverse AP. P inverse AP. Okay, so this implies that. Okay, so now see here P inverse AP. Okay, so what we want to prove? A is related to B. That means what? A is related to, you want to prove that B is related to A now. B is related to A. Symmetric means what? B. That means what? There exists an invertible matrix P such that what? P is equal to Q, A, Q inverse. Whatever this. Q may be different, no problem for this one, right? So you want only the P, this is not the restriction on the P. There should be the invertible matrix. Anyway, invertible matrix is allowed here. Okay, so you want to prove there is an invertible matrix Q or P such way that what? B is equal to Q. This you want to prove, right? With the help of this relation. So what will do? So you want to prove that this is not. You want to prove that A is equal to Q B Q inverse this. Okay, you want to prove this one. This one you have to prove. This we have. B is equal to P inverse AP. We have. You have to prove B is equal to Q inverse PQ. Okay. So how we can do this one? So now see, you want here P, I can multiply by P and I can multiply by P inverse, okay, because P is the invertible matrix. So I can write this what P, B, P inverse, okay. What we get then? So this is what, so we have to multiply by P inverse A, and this is what P and P inverse, okay. So now the associative law, it exists for the product of the matrices. So this is what P B P inverse is equal to. This is what P inverse. This is A. P inverse. We know that P is invertible matrix. That means what P into P inverse is the identity matrix. So I can write this as what P inverse of inverse. We know that inverse of the inverse is itself. So this is what P inverse is equal to. So this is what identity matrix A, and this is also identity matrix, right? So identity matrix into the matrix is itself now. So I can write this is what A is equal to P inverse of inverse A B into P inverse. Okay. So I may write no need to write actually. So that means what your invertible matrix is P inverse now. Your invertible matrix is P inverse. So that means what does this imply? We have proved that there exists an invertible matrix P inverse such that A is equal to P inverse of inverse. That means what? If you say P inverse is equal to Q, then what we get is A is equal to Q inverse B Q now here, right? So same type of this one, P inverse A P. So your P inverse is your Q now. So that means correct. If you write P inverse as P now, so what will there in P inverse? A B P. Okay. So that means what here? A is related to B is related to A. This is what? This implies that B is related to A. B is related to A. And this implies that feeder is symmetric. Feeder is symmetric. Okay? I call this as B now. Okay? Now we have to prove this is transitive now. Okay? So we prove it is transitive. Third, transitive. Okay? Okay. So that A is related to B, B is related to C. Okay? So A is related to B. So that means what this implies that uh, B is equal to P inverse A P, and here what C is equal to. So what we do? Is it correct? B is equal to C is equal to, okay, C is equal to what? Q inverse B Q now. Okay, where P and Q are invertible matrices. Invertible matrices. Okay. So now what you have to prove? You have to prove A is related to C. A is related to C. That means you have to prove there exists a inverse. It is that C is equal to what? Suppose this is R inverse A R. This you have to prove. There exists a invertible matrix R such that C is equal to R inverse A. This you have to prove. Okay. So now here what this implies that C is equal to Q inverse. So value of B, I will put value of B here. What? P inverse A P Q now. Okay. So this implies that C is equal to Q inverse P inverse A. So this is what PQ. This is equal. You know that AB inverse is same as what? B inverse into A inverse. Okay. So you know this. This is you know also this is what AB transpose is same as B transpose into A transpose. B transpose into A transpose. Right. So we'll apply this now. We'll apply this. Okay. So AB inverse is equal to what? B inverse into A inverse. Now this is what? Q inverse P inverse. So this implies that C is equal to PQ inverse now. Right. So PQ inverse is what? Q inverse into P inverse. So A PQ. Now see your P is now here P, right? So what does this imply? That A is related to C, and this implies that feeder is transitive. Feeder is transitive. So this implies that okay, I will call this as C now. Okay. So from ABC, from A, B and C, either is an equivalence relation. Either is an equivalence relation. So the problem is over. So this is also a very simple problem. So if you understand the inverse, if you understand what is meant by equivalence relation, how to prove that it is reflexive, how to prove that it is symmetric, how to prove that it is transitive, right? So then the problems are very easy. Okay, so we take one more problem. Let x is equal to n cross n. N means what? This is the standard notation of the set of the natural number. Okay, so the x is n cross n. Will define feeder on x, define feeder on x as AB related to CD if and only if AD is equal to BC. Show that feeder is an equivalence relation. Feeder is an equivalence relation. Okay, so we'll prove this. Okay, solution. Given that x is equal to n cross n. Okay, define feeder on x as this. Okay, so we have given this. Okay, so first this is given to you. Okay, so first what? Reflexive. So reflexive is what? What we have to prove? AB is related. This you have to prove. What? AB is related to AB. So how AB is related to CD? What? A. This is the first and second product of the first and second. So this is AB, right? And this is what? BC. BC means what? This is second into first. Second into first is what? BA. Right? So AB is equal to BA. This is true because A and B are the natural number. You know that the product of two natural numbers is the rational number, right? Since AB is equal to BA, so this implies that AB is related to AB. That means what? Every element is this is true for all AB belong to this. This is true for all AB belong to X, right? So therefore, this implies that feeder is reflexive. We call this as A. Then second, symmetric. Okay. So let AB is related to CD. What is this? What we want to prove? CD is related to AB. This you want to prove. That means what we have to prove? See the AB is related to CD means AD. So this is what? CB. This is CB. Then second and first. This is DA. This you want to prove. Okay, so what we have this AB is related to CD. So AB is related to CD means what? AD is equal to first and the last one, and second one is the first one, BC. Right? So we can interchange the places. BC is equal to AD. So these are the natural number. A, B, C, D all are the natural number. Product of the natural number is commutative. So you can write this is what? CB. This implies that CB is equal to DA. And this implies that CD is related to AB. CB is related to AD. And this implies that feeder is symmetric. We call this as B now. Okay. Now we have to prove this is transitive. We have to prove that it is transitive. Third one. Okay. So let AB is related to CD and CD is related to EF. Okay. So we write the meaning of this one. What? This A into D is equal to BC, and so C into F is same as D into E. is it. So now see what we want to prove. What we want to prove? AB is related to EF. This we want to prove. That means what? AF is equal to B. AF is equal to B. This we want to prove with the help of this one. With the help of this one. So what we do? We'll take the product of LHS at LHS and we'll take the product of the RHS at RHS. So what we get then? We'll take the product of LHS. One ADCF. Then this is one BCDE. BCDE. Now see, your ABCD are the natural number. That means they are not equal to 0. You can cancel this. Okay. So what here D get cancelled. See, D is there. C is also there. D, they are cancelled. Okay. So this implies that AF is equal to B. Right. So we get AF is equal to B. And what does this imply then? AB is related to EF. And what does this imply? Feeder is transitive. Feeder is transitive. We call this as C. So from A, B, C, from A, B and C, feeder is an equivalence relation. Feeder is an equivalence relation. So very simple problem. Okay, so let x is equal to R2. Let x is equal to R2. Okay, define xy related to AB if and only xy is equal to AB. If and only fy is equal to AB. Show that feeder is an equivalence relation. Also find equivalence class of 1 1. Also find equivalence class of 1 1. Okay, we'll write the solution given that x is equal to R2, xy is related to AB if and only this. Okay, so first reflexive. Okay, so what we have to prove? Xy is related to xy. Okay, so when we say that xy is related to xy, so see the product of the this xy, this is same as xy. This is also true. Xy is same. Since xy is equal to xy, so this implies that xy is related to xy for all xy belong to x, right? So therefore this implies that feeder is reflexive. For reflexive part is very easy. Reflexive. We call this as A now. Okay. Now second is what? Second, symmetric. Okay. So what we have to do? We have to assume that xy is related to AB, and what we have to prove? AB is related to xy. Okay. So let xy is related to AB. What does this imply? Xy is related to AB. Xy is equal to AB. I can write this is what AB is equal to xy. AB is equal to xy. So what does this imply? This implies that what? AB is related to xy. So what we have did? Xy is related to AB, and what we have proved? AB is related to xy. So that means what? Your feeder is symmetric. We call this as P. Okay. Now third one, transitive. Okay. So for transitive, we have to assume that A is related to B, B is related to C. Then we have to prove A is related to C now. So what? So let xy is related to AB. Okay. AB is related to CD. I will take this. Xy is related to AB. AB. So what does this imply? Xy is equal to AB. So and this is what? AB is equal to CD. What we want to prove? If we want to prove that xy is related to xy. So do this calculation. What we have to do? Okay, so xy is related to CD. Means what? Xy is equal to CD. This you want to prove. You want to prove with the help of this one. Okay. So now this is what then xy is equal to AB. AB is equal to CD. Means what? Xy is equal to AB is equal to CD means xy is equal to AB is equal to CD. So this implies that xy is equal to CD. Right? This we want to prove. That means what? Your xy is related to CD. Right? This we want to prove. So what does this implies? Theta is transitive. Theta is transitive. Okay. I call this as C now. Okay. So from A, B, C, from A, B and C, theta is an equivalence relation. Theta is an equivalence relation. And you want to find the equivalence class of 1 1. Okay. Equivalence class of 1 1. We will find equivalence class of 1 1. Okay. So you know that equivalence class of 1 1 is denoted by like this 1 1. So this means what? Set of all ordered pairs xy belongs to x such that xy is related to 1 1. Right? So this is means what? The set of all xy belongs to x such that xy is equal to 1. Okay? Just this is only. Okay? So this will be your equivalence class. Now we'll take the next problem. Let theta be a relation on Z defined by x is related to y, if and only if 5x plus 6y is an integral multiple of 11. Show that theta is an equivalence relation. Okay. So this is very interesting problem. So solution. Given that theta is a relation on Z defined by x is related to y if and only this. Okay. So 1. So now see, this is integral multiple of 11. That means 5x plus 6y is equal to 11 times some integer. Okay, it's 11 times some integer. Or this is what 5x plus 6y is divisible by 11. Is divisible by 11. Okay, so this way is one. So what we have to do? So x is reflexive. Okay, so reflexive. So what we have to prove? X is related to x. X is related to x is what? 5x plus 6x is the multiple of 11. See, 5x plus 6x is equal to 11. So every number is multiple of itself now. So is integral multiple of 11. Okay. So therefore x is related to x. So this implies that theta is reflexive. We call this as A. You may call this as 1 also. Now second, symmetry. So let x is related to y. This implies that what? 5x plus 6y is an integral multiple of 11. So this implies that I write this word 5x plus 6y is equal to 11 times m. Okay, so m belongs to Z. Integral multiple of 11. That means what? 11 times some integer. Okay, so now what we want to do? We want to prove that y is related to x. We want to prove that y is related to x. So that means you have to interchange the places. So that means what you have to prove? 5x plus 6x. 5x 5y plus 6x is integral multiple of 11. So we have 5x plus 6y is equal to 11 times m. Okay. So now, okay. So we do this for 5x plus 6x, 5y plus 6x. How we can do? I want to take this as 11. So what? I will write this as what? 5x plus 6y. I will write this 5x plus 6y. Okay. Now here what? There is a 6x. There is 6x. So and here there is only the 5x. So what we will do? I will write this as what? I will write this as a minus 5x. I will write this as minus. Okay. Minus this one plus 11x. So if I write this, what we get then? See, this is what 6x. Okay. So minus 5x plus 11x is 6x. Okay. I write minus of this one. I write minus of this one. Okay. Now here what? Minus 6y. But I have the 5y. So if I write 11y here also, 11y. Right. So that means what? If I write minus 5x plus 11y is equal to 11 to this. So what is this then? So 5x plus 6y is already known to you. This is a multiple of 11. So 5x plus 6y is 11. So this is what? Minus 11m plus 11x plus 11y. So if I take 11 common, so what we get? I will write this as x plus y minus m this. Right? Now your x is integer. Right? Because your relation is on. Right? So your x is integer, your y is integer, your m is also integer, and sum or difference of the integer is also integer. So that means what here? X plus y minus m belong to z. So what we have proved? 5x plus 6y and 5y plus 6x is the integral multiple of 11. So then this implies that 5y plus 6x is integral multiple of 11. So this implies that hidden is symmetric, or this implies that y is related to x. Y is related to x. Right? So this implies that hidden is symmetric. I call this as B. This is very important now here. Right? This part is very important here. Okay. Now we do reflexive. Reflexive we did. Symmetric we did. Now we have to do the transitivity now. Transitive. Third part. This is very important. The example is also very interesting now. Transitive. Okay. So let x is related to y is related to z. So this implies that I directly write this what? X 5x plus 6y. Okay. 5x plus 6y is equal to 11 times m. And this is what? Your x is y here now. So 5y plus 6z is equal to 11 times n. So your m n belongs to z. Your x, y, z are already integers, because what? We have defined the relation on z. Okay. So now what we want to prove? What we want to prove? X is related to y, y is related to z. So you want to prove that x is related to z. Means what we have to prove? So this is what? 5x plus 6z is some 11 times some integers. 11 times some integers. Integers not. Integer. Okay. 11. That is integral multiple of 11. This we want to prove. Okay. So with the help of this one, I have 5x plus 6y. I have 5y plus 6z. They are the integral multiple. What I have to do? I have to write 5x plus 6z as an integral multiple of 11. So how we can write this? So I will write this what? I want to do this. Okay. So I will write this. I want to express this 5x plus 6z in terms of this one. So how we write this is what? So I will write this is what? 5x plus 6y, and I will write this 5x plus 6z also. I will write this also. Okay. So what happened then this? What happened this? Okay. So your 5x is there now, right? And your 6z is also there. Only problem of y is there. Only problem of y. This is what? If I write here what? Plus, then this will what? The 11 times y, and that we don't want. That one. So I will write this what? Minus 11 times y. Now if you simplify this, you have to write this in terms of this now. So I have written this is what? 5x plus 6z in terms of this one. There should be the 5x plus 6y, because without this you cannot prove this one. Right? without, because you have to use x is related to y is related to x. That means we have to use these two terms. With the help of these terms, you cannot do this one. So what I have adjusted this, what I have converted this phi x plus cz in terms of this, right? So this is in terms of this. So now 6 minus 11. Simplify this. We don't need to simplify, but if you simplify this, we must get phi x plus 6z. So see this phi x plus 6y. So if you open the bracket, then this is what phi x plus 6y plus phi y plus 6z. So phi x plus 6z there. So this is what 11y and this minus 11y get cancelled. That means you get phi x plus 6z. So we are good. So this is what then 11 times m plus this is what 11 times n. This is minus 11 times y. Now you have to take your, what is your m? If you take 11 common, right? So each term contain 11, so that you can take 11 common. So I converted this phi x plus 6y in terms of each term contain the 11. So this is what 11. So this is what m plus n minus 1. Your m is integer, n is integer, your x, y, z are all integers, right? So that means what your m plus n minus y is also integer, because sum of 2, 3 integers is integer. Sum or difference of integers is an integer. Okay. So therefore what phi x plus 6z is the integral multiple of this. So this implies that x is related to z, and this implies that theta is transitive. Theta is transitive, right? So we call this as C. Okay. So from A, B and C, theta is an equivalence relation. So we are two. So again, very simple. We have to use only the idea, some calculations, and the knowledge, not about 10 actually. Okay. So below 10, we have to use the knowledge below 10. Okay. So we'll take one more problem. Let theta be a relation defined on Z. X is related to y if and only x minus y is an integral multiple of 5. Show that theta is an equivalence relation. Theta is an equivalence relation. Okay, solution. Okay, let solution. Given that x, y belong to z, x is related to y if and only this. Okay, so 1 reflexive. So I write this single y, 1. Okay, reflexive. What do I prove? X is related to x. Means what? So you cannot take x is related to x. We have to prove this x is related to x. So x minus x is what? 0. X minus x is equal to 0. I can write this is what? 0 into 5. Right? So this implies that x is related to. So 0 is integer. Therefore x is related to x. This implies that it is reflexive. Right? Because what? X minus x is the integral multiple of 5. So 5 times some integer. Right? 0 is one integer. So that means it is reflexive. Second, symmetry. Okay? So that x is related to y. What do I have to prove? Y is related to x. We have to prove. So x related to y means what? X minus y is equal to 5 times m. M belongs to z. I can directly write this. Okay. So now this is implies that what? Y minus x is equal to minus 5m. So this implies that y minus x is equal to 5 into minus m, right? So your m is integer, your minus m is also integer. Okay, because integers are nothing but 0 plus or minus 1. That means 1 is integer, minus 1 is also integer. 2 is integer, minus 2 is also integer. So same thing, your m is integer, minus m is also integer. So y minus x is the integral multiple of 5. So this implies that y is related to x, and this implies that reader is symmetric. Reader is symmetric. We call this as B. We call this as A. Next, third one, transitive. Transitive. Okay. So transitive. So let x is related to y related to z. What does this imply? X minus y is equal to 5 times m. Y minus z is equal to 5 times m. So this m and n, they are different now here. Okay. So your mn belongs. This is very important. Mn belongs to z. Right? You must have to write it mn belongs to z, because what m and n are not in the problem. Okay. So that is what you should mention. What are your m and n? Okay. So now what you want to prove? X minus y. You want to prove x is related to z. What does it imply? X minus z is equal to 5 times some integer. So we'll write x minus y now. X minus z. We'll write x minus z with the help of x minus y and y minus z. So you should express x minus z in terms of x minus y. So I write this what x minus y, and y minus z also I write. Okay. Now if you open the bracket, so what happened then? If you open the bracket, so what is this? If I write the plus sign here, so what we get then? This is x minus z. Now this is what then? This is your 5m plus this is your 5n, right? So it is very easy. You have expressed this x minus z in terms of x minus y, y minus z, like this. Okay. So now I can take this 5 common. So this is m plus n. Okay. So now your m plus n is integer, because sum of two integer is integer. So m plus n is integer. Therefore your what? X is related to z. This implies that. So this implies that reader is transitive. Reader is transitive. I'll call this as C now. So from A, B, C. So from A, B and C, reader is an equivalence relation. So the problem is over. Okay. So I hope that you understand the relation now, right? So the relation, we have seen the type of the relation, we have seen the equivalence relation, right? So this is also a type of the relation, right? So this relation part is over here now. So in the next time we will see what do we mean by function. Function is also a relation. Okay. So there should be the condition. For here what? For relation there is no condition. Every element of there is no restriction on the relation A to B now, right? So but under some condition, so that relation may be a function. So in the next part we will see what do we mean by function. Note that a function is nothing but a relation. Okay. So under some conditions, if some conditions are hold, then that relation is a function. So that we will be see in the next part. Okay. So now we will stop here. So okay, thank you.